So good morning everyone. In the previous class we had solved few numericals on how to compute the system entropies and mutual information. So in today's class we'll be discussing symmetric channel or uniform channel. So in the numericals discussed in yesterday's class we computed system entropies like h of x, h of y, h x by y, h y by x and joint entropy h x comma y, as well as mutual information I x comma y. So in today's class we'll be discussing symmetric channel or uniform channel. So a channel is said to be symmetric or uniform channel if the second and the subsequent rows of the channel matrix contain same elements as that of first row, but in a different order. So channel is said to be uniform or symmetric if the second row and the subsequent rows of channel matrix has the same elements as that of first row, but the elements will be arranged in a different order. For example, consider a channel matrix P of y by x. We have three symbols transmitted, x1, x2, x3. And at the receiver, we receive three output symbols y1, y2, y3. So the first row elements are 1 by 2, 1 by 3, 1 by 6. The subsequent rows will also have same elements as that of first row. The subsequent rows will also have same elements as that of first row, but they will be rearranged in a different form. So first row elements are 1 by 2, 1 by 3, 1 by 6. You can observe the second row. So we have 1 by 2, 1 by 3, 1 by 6. Same elements as that of first row, but the elements are rearranged in a different form. Similarly, even the third row has the same elements 1 by 2, 1 by 3 and 1 by 6, but the elements are arranged in a different form. So channel is said to be uniform or symmetric if the first row elements appear in the subsequent rows but in a different form. So we have one more example, P of B by A, that is a channel matrix. So first row elements are 0.5, 0.3, 0.2 and 0. So if you observe the second and third row, it has same elements as that of first row, but the elements are arranged in a different form. So this channel diagram is for P of y by x and the second channel diagram is for P of B by A. So this is a generalized channel matrix for a uniform channel. So you can observe the channel matrix elements. First row elements are P1, P2, P3, so on, PS. If you observe second row, it has same elements P1, P2, P3, so on, PS. But the elements are rearranged in a different form. So each row will have same elements P1, P2, P3, so on till PS. Each row will have same elements, but these elements will be appearing in a different form. The order of the elements will be different. compared to the previous rows. So we know that sum of all the elements of any row in a channel matrix is equal to unity. Sum of elements in any row for a channel matrix is always equal to 1. So if we add the elements of channel matrix of any row, it will give us a unity value, that is 1. So this row varies from j equals to 1. The first row element is j equals to 1, j equals to 2, so on, j equals to s. So summation j equals to 1 to s, p of b by a equals to 1. That is sum of elements in any row of a channel matrix is equal to 1. But all the rows, so totally we have r number of rows, a1 to ar. So these many rows will be having. So all the r number of rows have same elements as that of first row. Hence, this equation can be rewritten as summation j equals to 1 to s, p subscript j equals to 1. Each row has same elements, therefore this term is replaced with p subscript j. And in the previous class we had written equation for h of b by a, that is summation I equals to 1 to r, summation j equals to 1 to s, p ai comma bj log of 1 divided by p of b by a. B is the output symbol, subscript is j, a is input symbol, subscript is I. And from probability theory we know that p of a comma b is p of b by a into p of a. So this p ai comma bj is replaced with p of ai into p of b by a, that is b subscript j divided by a subscript I. P of a comma b is replaced with p of b by a into p of a. A has a subscript I, b has a subscript j. So since r number of rows have same element, so this equation 1 can be represented as summation j equals to 1 to s, p subscript j equals to 1. So p of bj by ai is replaced with p subscript j. Even this term is replaced with p subscript j. And summation I equals to 1 to r, p of ai is equal to 1. Sum of probability of all the inputs is equal to 1. So we'll be left with only this term. And if you observe the equation, this is same as the entropy equation, summation p log of 1 by p, where j varies from 1 to s symbols. So this is nothing but entropy and it is represented by h, which is constant, which remains same for all rows. Why it remains same for all rows? Because each row has same elements p1, p2, so on, ps. Suppose p2, p3, so on, ps. So each row has the same elements as that of first row, but the elements will be arranged in a different form. So if we add all the elements of each row, we'll be getting same value. So h of b by a is nothing but 1 into h. Summation I equals to 1 to r. P of ai is 1. 1 into h. So mutual information I of a comma b is given by h of b minus h of b by a. So h of b by a is nothing but equal to h. Therefore, channel capacity can be written as C equals to maximum of mutual information. Since H is a constant, so channel capacity is equal to maximum of H of B. And this H of B is nothing but output entropy. That is, we have S output symbols. So C equals to maximum of H of B. H of B is output entropy, which is determined by knowing the probability of S output symbols. So maximum of H of B is represented as log S. Why log S? Because we have S output symbols. Knowing the probability of S output symbols, we can compute what is the output entropy. Therefore, channel capacity is log S minus H. Channel capacity is given by C equals to maximum of mutual information. And the equation for mutual information is H of B minus H of B by A. And H of B by A is H. Maximum of H of B is log S minus H is the equation for channel capacity. So channel capacity for uniform or symmetric channel. So when we say the channel matrix is symmetric or uniform, if the subsequent row elements are same as first row, but the elements appear in a different form, then we say it is uniform channel or symmetric channel. So consider an example. For the channel matrix shown, find the channel capacity. So the given matrix is a channel matrix. So you can observe the first row elements are 1 by 2, 1 by 3, 1 by 6. Second row elements are also 1 by 2, 1 by 3, 1 by 6. Even third row has the same elements. Second and third row has the same elements as the first row but arranged in a different form. Hence, it is a uniform channel or symmetric channel. So we need to determine the channel capacity. And we know that channel capacity is log S minus S, H. We know that channel capacity for a uniform or symmetric channel is given by log of S minus H. S represents number of output symbols. If you observe the matrix, we have 3 output symbols and 3 input symbols. 3 output symbols. So log of 3 to the base 2. And we need to compute what is H. H is nothing but entropy. What is the equation for H? Summation J equals to 1 to S P subscript J log of 1 by P subscript J. So since uniform channel or symmetric channel elements remains same for every row, but the elements will appear in a different form. So each row of uniform or symmetric channel has the same elements, but the order is different. What are the elements of uniform or symmetric channel? 1 by 2, 1 by 3, 1 by 6. So entropy H is 1 by 2 log 2 to the base 2 plus 1 by 3 log 3 to the base 2 plus 1 by 6 log 6 to the base 2. Same thing is written over here. Each row has the same 3 elements. So therefore H is P into log of 1 by P. Consider the elements. Symmetric channel and we obtain H as 1.4591 bits per symbol. S value is 3 because we have 3 output symbols. Log 3 to the base 2 and we obtain H as 1.4591. Therefore, channel capacity is 0.1258 bits per second. So consider one more example wherein a channel matrix is given and we have to compute the channel capacity. See, if you observe the row elements, first row is having 0.6, 0.2, 0.2. Second row also has 0.6, 0.2, 0.2. Third row is also having same elements 0.6, 0.2 and 0.2. Second and third row has same elements as that of first row, but the elements are placed in a different order. Hence, it is a uniform channel or symmetric channel. And how do we compute the channel capacity for symmetric or uniform channel? For symmetric or uniform channel, channel capacity is given by log S minus H. We have 3 output symbols. S represents output symbols. Therefore, this will be log 3 to the base 2 and minus H. Equation for H is summation J equals to 1 to S P subscript J log of 1 by P subscript J. So we have 3 elements 0.6, 0.2 and 0.2. 0.6 log 1 by 0.6 plus 0.2 log 1 by 0.2 plus 0.2 log 1 by 0.2. Both these can be clubbed by neglecting last one and using a multiplication factor 2. So this will give us H value as 1.371. 0.6 log 1 divided by 0.6. We have the elements of each row as 0.6, 0.2, 0.2. Therefore, lowercase h, that is entropy, can be written as 0.6 log 1 by 0.6. 0.2 is appearing 2 times. 2 into 0.2 log 1 by 0.2. Therefore, H is 1.371 bits per symbol. And hence channel capacity C is log of S minus H. 3 output symbols, so S equals to 3 log 3 minus substitute h value, and the symbol rate is given as 1000 symbols per second. Therefore, channel capacity is log of s minus h into rs bits per second. Symbol rate is 1000. Therefore, channel capacity is 214 bits per second. So if you just write C equals to log of S minus H, indicates by default this symbol rate is 1 bit per second. But in the second example we solved, symbol rate is 1000. So 1000 into log of S minus H, which will give us channel capacity as 214 bits per second. So example 3, determine the capacity of channel for the figure shown below. So a channel diagram or the noise diagram is given to us. So from channel diagram or noise diagram, we can write the channel matrix P of y by x. We have 4 input symbols, x1, x2, x3, x4. 4 output symbols, y1, y2, y3 and y4. x1 to y, x1 to y2 value is 1 by 2. We do not have connections from x1 to y3, x1 to y4 value is 0. x2 to y2 1 by 2, x2 to y3 is 1 by 2, others 0. x3 to y3 1 by 2, x3 to y4 is 1 by 2. x4 to y4 is 1 by 2, x4 to y1 is 1 by 2. So this is the channel matrix we obtained for the given channel diagram or noise diagram. So now we need to determine what is the capacity of channel. So if you observe this given channel matrix, first row elements are 1 by 2, 1 by 2, 2 zeros. Second row also has 2 zeros and 2 1 by 2 elements. Third row also has 2 zeros, 2 1 by 2 elements. Last row also has 2 zeros and 2 1 by 2 elements. Hence it is or symmetric channel. So for uniform or symmetric channel, channel capacity C is given by log of S minus H. S represents number of output symbols. So we have 4 output symbols. So log 4 to the base 2 minus H. So how do we compute H? Summation J equals to 1 to S P subscript J log of 1 by P subscript J. So the uniform channel has 4 elements, 2 zeros, 2 1 by 2 terms. So 0 into anything will give us 0. So you can discard these two. First element is 1 by 2 log, and the second element is also 1 by 2 log 1 divided by 1 by 2. So this is nothing but 1 by 2 log 2 to the base 2 plus 1 by 2 log 2 to the base 2, which gives us h as 1 bit per symbol. Same thing I have computed here. Therefore, channel capacity is log of s minus h. S value is 4. Log 4 to the base 2 minus h value is 1. Log 4 to the base 2 is 2 minus 1. Therefore, channel capacity is channel capacity is 1 bit per symbol. So for third example, symbol rate is not mentioned. So it represents symbol rate RS is 1 bit per second. So which gives us channel capacity as 1 bit per symbol. So next example, a channel has following characteristics. P of y by x equals to 1 by 3, 1 by 3, 1 by 6, 1 by 6. 1 by 6, 1 by 6, 1 by 3, 1 by 3 are the second row elements. So the second row has same elements as that of first row. And the elements are placed in a different order. Hence, the given channel matrix is a uniform channel or symmetric channel. So for the given channel matrix, we need to compute h of x, h of y, hx comma y, and finally channel capacity if R is 1000 symbols per second. So we have two input symbols, x1, x2, 4 output symbols. So in order to compute h of x, h of y, hx comma y, we need a JPM matrix. But the given matrix is a channel matrix. So we need to convert it to a JPM. Since we have only two inputs and it is a symmetric channel, so the input probabilities are P of x1 is 0.5, P of x2 is 0.5. Probability of x1 input symbol is 0.5. Probability of x2 input symbol is 0.5. So now we need to convert this channel matrix to JPM. JPM is represented as P of x comma y. We have two input symbols, 4 output symbols. So we need to convert channel matrix to JPM. So we know that P of x comma y can be computed as P of y by x into P of x. We have P of y by x matrix form. Multiply it with probability of input, that is x. We'll obtain P of x comma y, that is a JPM. So first row should be multiplied with probability of x1. Second row should be multiplied with probability of x2. First row multiplied with probability of x1, that is 1 by 2. Probability of x2 is 1 by 2. So 1 by 2 into 1 by 3, 1 by 6. 1 by 2 into 1 by 3, 1 by 6. 1 by 2 into 1 by 6 is 1 by 12. Fourth element is also 1 by 12. So second row, multiply it with probability of x2, that is y2. Second row has to be multiplied with probability of x2, that is 1 by 2 itself. 1 by 2 into 1 by 6, 1 by 12. 1 by 2 into 1 by 3 is 1 by 6. So this is the JPM we have obtained by converting the channel matrix. So we know probability of x1 is 1 by 2, probability of x2 is 1 by 2. That is input symbol probabilities is computed now. So now we can compute what is h of x. If we know what is the probability of input symbols, we can compute input entropy. To compute output entropy, we should be knowing output symbol probabilities. Now the next question is how to compute the probability of output symbol. From JPM property, by adding the elements column wise, we can compute probability of output symbol. So probability of y1 is 1 by 6 plus 1 by 12. Probability of y2 is also 1 by 6 plus 1 by 12. So by adding column wise elements, we can compute what is the probability of output symbols. So which gives us 3 by 12, nothing but 1 by 4. So you can observe probability of y1 equal to y2 equal to y3 equal to y4 gives us probability as 1 by 4. So each output symbol probability is 1 by 4. So let us compute input entropy. We have only two input symbols, x1, x2, with probabilities 1 by 2. So h of x is 1 by 2 log 2 plus 1 by 2 log 2. Therefore, input entropy is 1 bit per symbol. And the probability of output symbol is 1 by 4. Therefore, h of y equals to all four output symbols have same probability 1 by 4. So it can be written as 4 into 1 by 4, 4 into 1 by 4 log 4 to the base 2. Therefore, we obtain output entropy as 2 bit per symbol. So now we can compute what is h of x comma y by referring the JPM. What are the elements of JPM? 1 by 6, 1 by 6, 1 by 12, 1 by 12. Therefore, hx comma y can be computed as 1 by 4 into 1 by 6 log of 6 plus 4 into 1 by 12 log 1 by 12. Therefore, joint entropy is 2.9183 bits per symbol. And the mutual information Ix, y is given by h of x plus h of y minus hx, y. H of x is 1, h of y is 2, hx, y is 2.9183. Therefore, channel capacity is 0.0817 bits per symbol. And for this uniform or symmetric channel, the channel capacity or the rate of transmission that is symbol rate is 1000 symbols per second. Therefore, C equals to channel capacity C is given by log of S minus H. We have 4 output symbols, log 4 to the base 2 minus H. How do we compute H? Summation J equals to 1 to S P subscript J log of 1 by P subscript J. So we have 3 elements in the JPM, 1 by 6, 1 by 6, 1 by 2, 1 by 2. Compute H, subtract, will get channel capacity. So channel capacity is 0.0817 bits per message symbol. Symbol rate is given as 1000 symbols per second. So 1000 into channel capacity. Therefore, total channel capacity is 81.7 bits per second. So this is how we compute the channel capacity for a uniform channel or a symmetric channel. So they give you a matrix, a channel matrix or a JPM. If it is uniform channel, then we need to compute the channel capacity. Channel capacity is given by log of S minus H, where S represents number of output symbols and H is computed as summation J equals to 1 to S P subscript J log of 1 by P subscript J. So this lowercase h is nothing but the elements of channel matrix. Substitute log S minus H gives us channel capacity. They may ask you to compute entropies as well as H of x, H of y, Hx, y. All these are computed by using JPM matrix. Similarly, mutual information Ix, y, Ix comma y can be computed by using any of the three formulas. Mutual information is nothing but h of x plus h of y minus h x comma y, or you can use I think it is h of x plus h y by x, or h of y plus h x by y. So any formula can be used to compute the mutual information. And the channel capacity of a binary symmetric or uniform channel can be computed as log of s minus h. S represents number of output symbols and H is nothing but entropy. And how do we compute this entropy? Consider the elements of channel matrix. That is the first row elements, because all the subsequent rows will anyway have the same elements.